So what we're going through here is the basics of neural networks. Then, because it is so visual, how can we use that to recognize features in images, and how can we project that onto text? How does that form the base or the foundation for LLMs and actually generating text ourselves, and then see if we can wrap up everything at the end. And just because I know we are academic engineers here in the room, so just to make this academically correct, artificial intelligence is basically anything where we try to use a computer to mimic human behavior. Within the field of artificial intelligence, we have something called machine learning, which is where we use statistical information to improve the way we do this. And then inside of that, we have machine learning based on neural networks. And this is typically what we refer to when we're talking about artificial intelligence. That is actually what we mean. Using neural networks to mimic the processes in the biological brain. But actually that is wrong. If we stick to academic terms, AI is much broader. But today we will be focusing on neural networks, at least for a start here. And since it is an attempt to replicate the human brain, let's just start by figuring out what it is the human brain actually does. And it's actually quite simple, at least at that level here, because using our senses, we receive some input, and based on that, the brain classifies this in some way, does some kind of classification, which kicks off the action or reaction that we do based on this. And all of this is based on the neuron. And the way the neuron works is actually, you should see this. So these antennas here at the end, you should consider each one of these little spikes mounted to a similar spike on another neuron, all of this forming a complete network and just sending signals all around. That's basically it's quite amazing. That's basically how neural activity works. And the whole idea is that when all the inputs here are stimulated enough, that makes all the outputs fire and sending signals throughout this network. Let's see if we can use this. So let's make a small exercise for which I will need 4 volunteers here. We're going to determine if the weather is so good that we can eat outside. Please step forward. So I'm going to give each one of you a very, very simple task. You should, based on the fact if the sun is shining or not, and yes, of course it is shining because it does shine, but if there is sunshine, the degree of sunshine, when we start, I will ask you to define that level on a scale from 0% to 100. How much is the sun shining today? The wind. How is the wind today, where 100% it is the worst storm ever, and 0, you could play ping pong outside? And then we have the next temperature. So you should just, let's say on a scale from 0 to 40 degrees, where are we? And you're looking at all these signals, and based on that, you will give me the probability between 0 and 100% for that we can actually eat outside. So please, gentlemen, take your positions. So the temperature.
Okay, sun. Yeah. Well,
sun. Sorry,
yeah,
sorry.
UV guy.
Yeah.
So from 0 to 100, that was the task. I would classify it as 25.
So please show that with your hand. 0, 100.
Yeah, that's 7.
Okay. Yeah. That's the wind. That's wind. Yeah.
12.
That's 12. So now you are looking at these signals, and what is your? So you would say that's about 45% chance of read. that we can eat outside. Okay, what we have just done now, you're actually a brain together here on stage. It's not the most complicated brain, because it has 4 neurons. And just to compare this, the human brain has estimated 100 billion neurons. So it's not the most complicated brain. But nevertheless, together you are a brain, and each one of you is 1 neuron. Thank you. You can sit down again.
Can I give you the Irish brain answer?
Yeah. yeah. However, I would like to add that while the 3 of you here, it was very like, let's say, objective. The temperature, that cannot really be argued. It is 12 degrees, period. But your way, or your estimation, if we could eat outside, that was probably based on some kind of weighing or bias you added to it, knowing that, okay, if the sun is shining and there is no wind, maybe it does not need to be that hot anyway. There was probably some kind of bias, which we will just keep for now. But before we continue, let's just take a very, very quick peek into how do we perceive the world around us. These 3 gentlemen, about 100 years ago, they formed what is being referred to as Gestalt psychology. And that is the ideas or the theory about how the human brain perceives the world around us. Or actually, it is about how the mind makes up what the senses feed into the brain. So, 1 of 4 simple rules here. There are many, many more. The rule of proximity. What the eye sees is 36 dots here. But what the mind sees is 3 or 4 groups of dots. That's the rule of proximity. What seems to be close together belongs together. The rule of similarity. What the eye sees is a series of dots, different shapes, different colors. What the mind sees is a line of squares and a line of different colored dots. There's a rule of continuity. What the mind sees here is actually some kind of curve. And then there's a rule of closure. The mind sees a ring here, though there is no ring. And it's actually pretty amazing because of these rules, we're able to see things that don't exist. Like, there are no rings here. This is not a panda until the rule of closure has been applied to the picture. These are illusions we have probably seen before. And when all of this works together, that is what allows us to see this, or actually to read handwriting. That is because the mind applies all of these rules. And once we start to play with this, we can make some quite amazing ideas out of it. What the eye sees here is actually just a whole lot of individual elements, but the mind sees something completely different. And once you have seen this picture here once, you will probably always recognize the baby lying down here. So what this is that the whole is other than the sum of elements when we perceive the world. And it's not just restricted to what we see. This is all our senses. This is what we hear too. And that's actually why you find harmony in music. It's because you hear the individual tones, but together it builds up more or something different than the individual elements. So, let's see if we can use inspiration from that to build a neural network. So we're going to do something that can recognize my poor handwriting here. And the way we're going to do this, inspired by Gestalt psychology, is that if we can somehow recognize these individual elements, we can with a high probability predict that we may have seen that certain character. So how are we going to do this? Well, we'll make a matrix around the character, like I do here, a 20 by 20 matrix. And I will assign each individual cell a value describing how much of that cell has been covered by the image. So obviously this one is not covered at all, and this one has been covered by 90%-ish. Then we're going to make, just as we did when we were trying to predict whether or if we can eat outside, we're going to assign one neuron to each one of these cells in the matrix, or each one of the pixels. So we have 400 neurons. Each one of them will raise the hand telling how much of the cell has actually been covered by that pixel. We call that the input layer. Then we introduce the middle layer, and the middle layer, that is Garth, determining if we can eat outside. The middle layer will look at all these percentage values from the input layer, and based on that, it will come up with a percentage, with a probability that a shape like that exists in the pattern, or a shape like that. So there will be one node, one neuron in the middle layer here for each shape we would like to recognize. And then finally we will have the output layer, which will look at these percentages from the input layer, and based on that, come out with a probability that we have seen these three shapes, and thereby there's a high probability that we have seen the letter or the number 2. So that is basically how it works. So we order the neurons in layers, and in each layer you just take in the percentages from the previous layer. Based on that, you define a probability, a likelihood, a percentage that you have seen some more advanced shape, which you can then pass on to the next layer. And this is exactly what we did in the weather exercise. And we could have done this handwriting thing too as an exercise where I would need 400 volunteers, each one being 1 pixel, then a number of volunteers for the middle layer and a number of volunteers for the output layer. We could have done that the same way. So please note that the structure and the number of neurons we had, that was very, very strongly defined by the actual use case we wanted to address here. If we want to do this with more advanced images, we need to dive a little deeper. So this is how it actually works. So the input image where we want to recognize certain objects. Imagine you're passing in a picture of something and you want to know if there's a tree or a dog in that picture. The way it works is we pre-process this picture. One way to do this is that we search for all lines, vertical, horizontal lines in it, and we can pass that on in the machine. So this is actually what happens inside these convolutional networks we can use to do such things, and what happens on your when you're taking a picture with your phone and it's trying to recognize eyes and remove red eyes and whatever. This is actually based on principles like that. So what it does is the same way as we just had with the handwriting characters. So we try to find the positions of vertical and horizontal lines, shadows, color transitions, everything. Based on that, we pass it on to the next layer, to see if that layer can recognize circles, simple geometric figures, edges, and so on, of which we can pass on to the next layer. So given that these shapes are present, what is the chance that we have seen certain surface structures, which we can pass on to the next layer? What is, based on that, what is the probability that we have recognized eyes and walls and leaves? And based on that, what is the probability that we have recognized whatever objects might be in the picture? That's actually how it works. This is a picture I found on NVIDIA's homepage, which shows that actually most of the magic in these frameworks is actually not the neural network itself. It is about preparing the data and doing all this filtering and trying to come up with edges and vertical lines and so on to be able to have something to feed in to the neural network. And then obviously there comes the big picture, or the big question. How do we connect all these neurons? How do we come up with these probabilities? How do we assign these numbers to these hundreds of thousands of neurons there must be here? And the answer to that is training. A lot of training. We let the network do it itself. So by showing a lot of pictures and telling the network what is actually present in that picture, it will eventually adjust all these values to be able to recognize what we're feeding into it. Lots of training. And this is the weights and biases we were talking about too, when you were probably assigning more weight to some input than to other input. This is actually what happens when we're training the network. And talking about training, so let's say I'm training this with, I want to teach my network if there's a dog in the picture. So I'm showing a couple of pictures with a dog. I'm telling it, there's a dog in that picture. I'm showing a couple of pictures with no dog, and I'm telling, no, there's not a dog in this picture. And then when I'm testing it, showing this picture. In this situation, there would actually be a high probability that it would tell me that there's a dog in this picture. Because please keep in mind, we don't know what it is the network is recognizing in the picture. We have just taught it to recognize lines and edges and shapes and whatever, but it has no knowledge about an actual dog. So there's a very, very high probability that if we use this as a training set, what it would see would actually be the sofa. And it would tell, yes, I know, when there are these shapes in a picture, I have learned there's a dog in the picture. So training is very, very important. Which also opens up the big question. So how do we recognize objects we haven't seen during the training? And the short answer is we don't. Because this is recognizing patterns and nothing else. So the ability of, or the level of common sense, or the ability to do associations is completely absent. It's not existing at all in this. This is pure pattern recognition. We recognize patterns and nothing else with neural networks. But wait. So if we can recognize patterns in pictures, we might be able to do so in text too. And if we could do so, we could make rules for the order of the words in the text we see. So, Garth, you're a native speaker. One of these sentences is wrong. Grammatically, which one?
As a native speaker, I don't have a damn clue.
Okay, I can tell you the first one is correct. And why is that? That is because the order of words, grammatically, That is the correct order of the words here. So quality should come before color, which means the sentence where quick appeared before brown is the correct one. How would you ever program this? How would you ever solve that if you were to program a piece of software that could do this? So the way we do this with neural networks is we assign each word a number. So in this case, we just feed the sentence in, and every time we see a new word, it's a new number. And every time we see a word which we have previously seen, it's the same number. So with that, we can set up probabilities for the order of the words, given that we feed a lot of text into this and we keep repeating the words. With that, we can set up rules for the probability of the order of the words. And if we can do so, actually we can not just recognize words. In that case, we should be able to produce sentences ourselves, because given the context so far, we know the probability of the next word to appear in the sentence. So, just to make this very short and very primitive, let's say we have he drives so far, and we have a list of words. Which one is the most likely one to be next? Well, it is his. So far, what would be the obvious word next given these probabilities, given these rules we have learned? Red, and so on. So if we have enough statistical material here, we should be able to build our own sentences. What has really been mind-blowing the past years is the GPT models, which is a machine learning model trained with incredibly huge data sets, which allows it to generate not just grammatically or syntactically correct orders of words, but also semantically. So it gives meaning. It's not just grammatically correct. It gives a meaning too. The evolution here has been, in 2018 we had GPT-1, and I'm just focusing on GPT here because that is something we all can relate to. But these models are not just restricted to GPT, these are LLM, large language models in general. Did you notice that you just applied the rules of Gestalt psychology to this? You heard a sound and you knew it was a glass on the floor. GPT-1 was trained on a lot of web pages plus 11,000 books. It had 117 million parameters, and it was way too limited and not really capable of producing anything meaningful at all. Then GPT-2 came, trained with much larger data sets. It had 1.5 billion parameters, and it could do more advanced and realistic sentences, but still not sounding natural in any way, what it did. Then we had GPT-3, which was trained on even more data. Wikipedia articles, you name it. It has 175 billion parameters, 100 times bigger than GPT-1, 10 times bigger than GPT-2, 96 layers of neurons in that model. And suddenly we could do these sophisticated language chats with it. But it didn't stop here. So now we have GPT-4, which is a huge improvement. The details are not really official yet, but most likely it has maybe more than 1,000 billions of parameters. It's a huge thing we have here. And ChatGPT, that's actually just an advanced piece of software based on the GPT model with a lot of filters to make it politically correct, and it cannot encourage to violence, to violent acts, and so on. But the training set in these models, that's still a significant limitation. Well, first of all, there's no updated knowledge since the training. And still, there are still fundamental rules in these solutions. I'm pretty sure if we started to have a conversation with ChatGPT about Biden versus Trump, I'm pretty sure a lot of filters would kick in. But it is frightening how realistic it has become. One thing I find a little bit scary actually is, first of all, it refers to itself as I. And every time you're interacting with these solutions, you're typing you to it as if it was a person. Our language, our own language, has not been able to follow the evolution here. We're still dealing with first, second, and third person in the way our language works. But this is not a person. Yeah.
Quick comment. I actually think that's a benefit because it gives you more natural interaction.
It does. It certainly does. Yeah. Yeah. I'm even tempted to add a please.
I do that too.
Yeah, to the input. It's completely irrational. There are no feelings at all behind this.
I think that's a generation thing. My daughter doesn't do that.
Yeah?
Just tells her what to do.
Okay, well,
It doesn't catch
yeah.
flies.
Does she add a please when she speaks to you? No. Here's an example. A real example I did, just to see, and this is still ChatGPT. This is not what we're going to talk about today. But just to see, does this thing really know everything? I had this piece of code. This is Erlang. And to be frank, I didn't know what it did. So I pasted this to ChatGPT asking, what does this piece of code do? And this is the reply. You don't have to read all the details here. But it basically says that it defines a string with a length of 6 with random numbers 0 to 9. That's pretty cool. So I decided to try to test the limits here. So, well, no, let me just first, when I looked a little bit closer to that and what it explains, I kind of stumbled over that 0 and 8 because it generates random characters between 0 and 9. So maybe we shouldn't trust this too much. But anyway, I forgot the please, but at least I remembered you. So I asked it if it could make an Alexia equivalent of that, and certainly, here it came. But now, the size, which was 6, has become 8. And blah, blah, blah. So I decided to, okay, let's see if we can find, let's just try. I want to find something more here. So can you do a Lisp equivalent? Yes, certainly I can. Same thing. Okay, what about Fortran? Well, now suddenly, at least it had the length correct here, and I'm unable to tell you if this actually works. But, and I know you're going to like this, Garth. So I figured out, okay, I'm an old fox in this game. When I first learned programming, that was in 6502 assembler. So I asked it to, can you make an equivalent of that? which it claimed to do, but I'm an old fox here, and I know CPY, that is an extended opcode in this language. This is not 6502 assembler, but I guess now we are becoming a little bit too nerdy. So, just to sum this up, a fruit fly, which basic purpose here on Earth is to be very annoying. The brain of that has 100,000 neurons. And you can think of what that is able to do, which is actually pretty advanced. What, besides being annoying, that is actually a living creature with 100,000 neurons. Just think of how many neurons we just needed to be able just to produce basic text. The human brain has estimated 100 billion neurons, and each of them is connected to hundreds, thousands of other neurons. The neuron, as far as we know, the biological neuron can fire in at least 26 different ways. Connections between them can come and go. The transmission time inside our mind corresponds to a clock frequency of 200 Hertz. And the total effect of our brain corresponds to about 20 watts. So you could say that the brain is an incredible 20-watt computer ticking at a very, very low clock frequency, but with millions of cores and a lot of transmission patterns. And it is estimated that for doing simple tasks, which both a computer and the human brain can do, that a computer will need 50 million times more energy to solve the same task. And by the way, the fact that the transmission time corresponds to a clock frequency of 200 Hertz, that is probably one of the limiting factors why our brains did not continue to grow, because the reaction time would simply be too long in the brain. The transmission time throughout the brain would not be good for our survival. The brain is too slow. But imagine if GPT had been trained on not thousands and thousands of books and Wikipedia articles and everything else, if it had actually been trained on code. So let's take a break, and this is where I will pass it on to you, Carl.